Hello everyone, welcome to another lecture in Machine Design 1. In this lecture, I'll be discussing about variable stresses in machine parts. In the previous module, we have discussed the stresses due to static loading only. But only a few machine parts are subjected to static loading. Since many of the machine parts, such as axles, shafts, crankshafts, connecting rods, springs, pinion teeth of the gear, etc., are subjected to variable or alternating loads, which is also known as fluctuating or fatigue loads. Therefore, we shall discuss in this lecture the variable or alternating stresses. In this lecture, I will discuss about the concept of cyclic stresses, fatigue and endurance limit, factors affecting endurance limit, and the factor of safety for fatigue loading. To understand the concept of cyclic stresses, let's consider a rotating beam of circular cross-section and carrying a load W. So it is denoted here that we have a load here, W, which is shown in the figure 6.1. This load induces stress in the beam, which are cyclic in nature. A little consideration will show that the upper fibers of the beam, for example at the point A, representing that this is the upper fiber, are under compressive stress when applied with the load W. And the lower fibers, such as at point B, are under tensile stress. After half a revolution, the point B occupies the position of point A. Alright? It occupies the position at point A, and the point A occupies the position of point B. So thus, the point B is now under compressive stress, and the point A is now under tensile stress. The speed of variation of these stresses depends upon the speed of the beam. So from above, we see that for each revolution of the beam, the stresses are reversed from the compressive to tensile. The stresses which vary from one value of compressive to the same value of tensile or vice versa are known as completely reversed or cyclic stresses. So please take note that the stresses which vary from a minimum value to a maximum value of the same nature, so for example, if it is either tensile or compressive, are called fluctuating stresses. Second, the stresses which vary from 0 to a certain maximum value are called repeated stress. Alright? And the third that we should take note is that the stresses which vary from a minimum value to a maximum value of the opposite nature, let's say from a certain minimum compressive to a certain maximum tensile, or from a minimum tensile to a maximum compressive, are called alternating stresses. Okay, so we can see here in these notes that there are three cases at which we say that there are cyclic stresses. It could be either fluctuating, repeated, or alternating stresses. So let's go to fatigue and endurance limit. So it has been found experimentally that when a material is subjected to repeated stresses, it fails at stresses below the yield point stresses. Alright? And that type of failure of a material is called fatigue. Okay. So this failure is caused by means of a progressive crack formation, which are usually fine and of microscopic size. The failure may occur even without any prior indication, and that the fatigue of materials is affected by the size of the component, relative magnitude of static and fluctuating loads, and the number of load reversals. Seen in figure 6.2 is a shaft after fatigue failure. We can see here a break at the cross-section and some progressive cracks near the two ends of the keyway. These cracks, if not attended, will eventually progress into a larger crack, which would be detrimental to the performance and safety of the machine. Now let's go to the time stress diagrams. So in order to study the effect of fatigue of a material, a rotating beam method is used. So you can look up of how a rotating mirror beam method is done through the link provided in the description. So you can see there how it is conducted and how the fatigue endurance limit are determined using this method. So by this method, standard mirror polished specimen, as shown in this figure 6.3a, is loaded in bending. So it is subjected to bending load. As the specimen rotates, the bending stresses or the bending stress at the upper fibers varies from maximum compressive to maximum tensile, while the bending stress at the lower fibers varies from maximum tensile to maximum compressive. In other words, the specimen is subjected to a completely reverse stress cycle. So this is represented by a stress or a time stress diagram as shown in 6.3b. Right? And the record is kept of the number of cycles required to produce failure at a given stress. And the results are plotted in stress cycle curve as shown in 6.3c. So in 6.3c we can see here a stress cycle curve. A little consideration will show that if the stress is kept below a certain value, as shown by the dotted line in C, the material will not fail whatever may be the number of cycles. So this is the limit of this dotted line indicates that whatever number of cycles, the material will not fail. The stress as represented in the y-axis of this graph is known as the endurance or fatigue limit, and it is represented by the notation sigma sub e. It is defined as the maximum value of the completely reversed bending stress which a polished standard specimen can withstand without failure, and for an infinite number of cycles. And the cycles, though it is said to be infinite, is usually 10 raised to the power of 7 cycles. It may be noted that the term endurance limit is used for reversed bending only, while for other types of loading, the term endurance strength may be used when referring the fatigue strength of the material. And it may be defined as the same maximum stress which can be applied to the machine part working under actual conditions. Alright. So we have seen that when a machine member is subjected to a completely reversed stress, the maximum stress in tension is equal to the maximum stress in compression as shown in figure 6.3b. Alright. So we can see here that there are the same values when we look into the maximum and minimum values of the stress, even in tension or in compression. So in actual practice, many machine members undergo different range of stresses than the completely reversed stress. Okay, so this is true in the actual practice. So the stress versus time diagram for fluctuating stress having the values such as the sigma minimum and the sigma maximum is shown in 6.3a. Okay. So the variable stress in general may be considered as a combination of steady or the so-called mean or average stress and a completely reversed stress component, sigma sub v. Okay, so this is the reverse stress component, and because of that, we can have the following relations derived from the, from the time versus from the stress versus time diagram. So for mean or average stress, which is denoted by sigma sub m, it is equal to the sum of half of the sum of the maximum and minimum stresses. And the reverse stress or the variable stress, which is represented by sigma sub v, is equal to the maximum stress sigma sub max minus sigma mean over 2. And for repeated loading, the stress varies from maximum to 0 in each cycle. So therefore, since the minimum value of the stress is for repeated loading is 0, we just simply substitute 0 in this formula. Thus, we have the mean or mean stress or the variable stress, which is simply equal to the sigma max over 2. And next is we have the so-called stress ratio. So stress ratio, denoted by capital R, is equal to the ratio of the maximum stress and the minimum stress. Where for completely reverse stresses, the value of the stress ratio R is taken as -1. And for repeated stresses, R is equal to 0. It should be noted that R cannot be greater than unity, or R cannot be greater than 1. Alright, so our next relation here is the relation between endurance limit and stress ratio. And this relation is represented by this expression, where the sigma E prime is equal to 3 times sigma E, or the endurance limit, over the quantity 2 minus R, where the sigma E prime is the endurance limit for any stress range represented by R. The sigma E is the endurance limit for completely reverse stress, and R is the stress ratio. And for variable stresses, there are a lot of factors that needs to be considered when solving for design stress or working stress of a machine member. So there are these factors to be considered may be dependent upon the size of the material, the surface finish of the material, and more obviously is the type of loading, or what load is subjected into the machine part. And the first of the factors that affects the endurance limit of a machine member is the loading, and this is called the load factor. So this first factor is the effect of loading on the machine member. So the endurance limit, sigma E, is of a material as determined by the rotating beam method is for reversed bending load. There are many machine members in actual practice which are subjected to loads other than reversed bending loads. So thus, the endurance limit will also be different for different types of loading. And the endurance limit, depending upon the type of loading, may be modified as discussed. Alright, so there are different types of loading that may be subjected into a machine member. Thus, we have these 3 types of a load correction factor. And the first load correction factor is the K sub B, or the load correction factor for the reversed or rotating bending load. And this value is usually taken as unity, or this value is usually assumed to be equal to 1. And the next load correction factor is the K sub A, or the load correction factor for the reversed axial load. And for usual practice, the value of K sub A is may be taken or usually taken as 0.8. And lastly, the other correction factor is the K sub S, which is the load correction factor for the reversed torsional or shear load. And for two possible materials that may be used for the machine member, there are two possible values that may be used for K sub S. Like for ductile materials, its value may be taken as 0.55, and for brittle materials, it is 0.8. Thus, we have the following relations to get the endurance limit for different types of loading. For endurance limit for reversed bending load, denoted by sigma sub EB, it is the product of the endurance limit for completely reversed stresses, sigma E, and the load correction factor, K sub B. And so, if K sub B is equal to unity, or 1, which is usually taken by the previous slide, sigma EB is just equal to sigma E. Alright, since K sub B is usually taken as 1, thus the endurance limit for reverse bending load is simply equal to the endurance limit of the material. Next is the endurance limit for reversed axial load, which represented by sigma sub EA is equal to sigma E, or the endurance limit, times the load correction factor, K sub A. So K sub A is the load correction factor for reversed axial loading, and the endurance limit is equal to sigma E. And for the endurance limit for reverse torsional or shear load, which is denoted by a tau sub E, is equal to sigma E. Sigma E, or the endurance limit, times the load correction factor for reversed torsional shear load, or the K sub S. In getting these endurance limits, one may take the value suggested above depending on the type of material. Alright. So the next factor that will affect the endurance limit of the material or the machine member is the surface finish of the material. So thus, we have this correction factor that is a result of the surface finish. And when a machine member is subjected to variable loads, the endurance limit of the material for that machine member depends upon the surface conditions. So these surface conditions refer to the type of finish of that machine member. Here in figure 6.4, we see the values of surface finish factor for the various surface conditions and the ultimate tensile strength. In this graph, the y-axis represents the values of surface finish factor for the different surface finishes. The x-axis is the ultimate tensile strength of the material in megapascal. So we can see here that there are different possible surface finish for a material. Like for example, if it is mirror polished, the value of the surface finish factor, regardless of the material's ultimate tensile strength, is equal to 1, equal to unity. And for different surface finish, like for example for polished, the value seems to decline as the ultimate tensile strength of the material increases. And also there are possible values here for different surface finishes. When the surface finish factor is known, then the endurance limit for the material of the machine member may be obtained by multiplying the endurance limit and the surface finish factor. We see that for a mirror polished material, the surface finish factor is unity. Alright, so let's go back here. The surface finish factor is equal to 1 or unity for mirror polished materials or machine members. In other words, the endurance limit for mirror polished material is maximum, and it goes on reducing due to surface condition. Then, if we let K sub SUR as the surface finish factor, then we can obtain the endurance limit sigma sub E1 as this as sigma sub EB times K sub SUR. So what is this K sub EB? This is the endurance limit for reversed bending load, and the K sub SUR is the surface finish factor. So since, as we discussed in the for the previous factor, this sigma sub EB is equal to the product of sigma E times the load correction factor for bending load. Therefore, the endurance limit sigma sub E1 is equal to sigma sub E times KB times K sub SUR. And since the value of the load correction factor for bending, or K sub B, is usually taken as unity or 1, therefore the value of sigma E sub E1 is simply equal to the endurance limit of the material times the surface finish factor. Meanwhile, for a machine subjected to reversed axial load, so for reversed axial load, the endurance limit is equal to sigma sub E times the load correction factor, K sub A, or the load correction factor for reversed axial load, and the surface finish factor. And the same is also the same concept is also used in determining the endurance limit when the machine member is subjected to reverse torsional or shear load. We just simply replace the value of the load correction factor to K sub S, or the load correction factor for reverse torsional or shear load, and we multiply it with the surface finish factor K sub SUR. So let's take note that the surface finish factor for non-ferrous metals may be taken as unity. Okay, so for non-ferrous materials, the surface finish factor is equal to 1. Next factor that will be discussed is the effect of size. So if a little consideration of the specimen, we show that if the size of the standard specimen, as discussed or shown in the figure 6.3a, so this is the standard specimen, is increased, then the endurance limit of the material will decrease. Why? This is due to the fact that a longer specimen will have more defects than a smaller one. Okay, so this sounds logical. So thus, we will let K sub SZ as the size factor. So then, the endurance limit for a machine member subjected to different types of loading is defined by the following expressions. Okay, so these are now the endurance limit of a material when we consider the size factor and the previous factors. Okay, in these expressions, all the factors are considered, and the factors corresponding to the type of loading is used in computing the endurance limit. Thus, we can see here that for reversed bending load, reversed axial load, and for reversed torsional or shear load, we simply use the corresponding load correction factors, the K sub E, K sub A, and K sub S respectively, while we also consider the surface finish factor K sub SOR, and thus we have the size factor K sub SZ. So place in considering the size of the specimen that is used in the rotating beam method, please take note that the value of size factor is taken as unity. So this is one of the things to be remembered in when you consider the size factor. The K sub C is taken as 1 for the standard specimen having nominal diameter of 7.657 millimeters. Okay. While if the nominal diameter of the specimen is more than 7.657 but less than 50 mm, the value of the size factor K sub SZ may be taken as 0.85. And lastly, if the nominal diameter of the specimen is more than 50 mm, then the value of size factor may be taken as 0.75. Alright. So, in addition to the surface finish factor K sub SOR, the size factor K sub SZ, and the load factors K sub B, K sub A, and K sub S, there are many other factors that may be considered for determining the endurance limit of a material. And these factors are the reliability factor K sub R, the temperature factor K sub T, and the impact factor K sub I. And all these factors has effect on the endurance limit of the material. And considering all these factors, the endurance limit may be determined by using the following expressions. For the reverse bending load, the endurance limit, or the sigma E prime, is equal to sigma E sub B times the K sub SOR times K sub SZ times K sub R, K sub T, and K sub I. So please take note that, or you simply observe that when considering these three factors, the reliability, temperature, and impact factors, you simply multiply these three factors into the previous expressions that we have just derived in the previous slides. Alright, so we can see here that we have just multiplied these three factors. So the same goes with the other types of loading. Say for the reversed axial load, where we obtained the expression for getting the endurance limit, or the sigma E prime. We have the corresponding size factor, corresponding load correction factor, and in considering the three miscellaneous factors, we simply multiply the three factors into the expression. And also the same with the reverse torsional or shear load. In solving problems, if the value of any of the above factors, so what are these factors? If in the problem it is not mentioned, or there are no discussion or even given values of the reliability, temperature, and impact factors, their values may be taken as 1. Alright? So next is the relation between endurance limit and ultimate tensile strength. So it has been found experimentally that the endurance limit, sigma sub E, of a material subjected to fatigue loading is a function of ultimate tensile strength. So in this figure, this shows the endurance limit of steel corresponding to ultimate tensile strength. So there are different endurance limit corresponding to the corresponding to the ultimate tensile strength of material, which depends uh, on the type of surface condition of the material. It may be ground, machined, hot rolled, or forged. And the different values of the endurance limits corresponding to the material's ultimate tensile strength. Okay, so we can see here these different conditions. So it is we can see here that uh, the highest values among the surface conditions is ground, and the lowest is the forge condition of the material. So there are empirical relations that is commonly used in practice. So for example, for steel, the endurance limit or steel is equal to the uh, 0.5 or half of the ultimate tensile strength. While for cast steel, the endurance limit is equal to the 40% or 0.4 of the ultimate tensile strength. For cast iron, the endurance limit is equal to 0.35 times the ultimate tensile strength. And while for non-ferrous metals or alloys, the endurance limit is equal to 0.3 of the ultimate tensile strength. These relations are some of the things that you need to be familiar with, as this will be useful in solving problems involving endurance limit. Okay, so you may need to memorize or simply get familiarized with these relations, such as these materials are commonly used in the industry, in practice, and also in solving machine design problems. Now, let us proceed with the factor of safety for fatigue loading. When a component is subjected to fatigue loading, the endurance limit is the criterion for failure. Alright? So for instance, fatigue denotes or connotes the failure of a material. Thus, it will be used. It will be used in the endurance limit will be used as a criterion for failure. So mathematically, um, the factor of safety is expressed as the ratio of the endurance limit stress to the design or working stress, and we know that the endurance limit stress is denoted by sigma E, and the design working stress is sigma sub T. Thus, getting the factor of safety when considering fatigue loading, Fs is equal to sigma E over sigma D. So take note that for steel, which is commonly used in practice, the endurance limit is usually equal to 0.8 to 0.9 of the yield point stress, where in this expression the sigma sub E is the endurance limit stress for a completely reverse stress cycle, and the sigma sub Y is the yield point stress. Now let's get into an example problem. So for this is the example problem 6.1, where we are given a piston rod. Okay, so determine the design stress for a piston rod where the load is completely reversed. The surface of the rod is ground, and the surface finish factor is 0.9. It is assumed that there is no stress concentration, the load is predictable, and the factor of safety is 2. So first is as mentioned in the problem, we are required to determine the design stress for a piston rod. And it is mentioned in the problem that the piston rod is subjected to completely reversed loading. So we know that a piston rod uh, is subjected to uh, a reversed and axial loading, right? And we are given here that the surface of the rod is ground. Thus, we can get on uh, it represents uh, the factor, and also the relation of the ultimate tensile strength. And we are also given the surface finish factor for of the material, and we are given with the value as zero point 0.9. So there's no stress concentration, and we are given with a factor of safety of 2. So for other factors, we will look if there are miscellaneous factors in the problem. So are there any miscellaneous factors like the reliability, temperature, impact factors given in the problem? So I believe there's none. Thus, we will assume or take the miscellaneous factors K sub R, K sub T, and K sub I as 1. Alright? So these are the given values. So the piston rod is subjected to reversed axial loading. Thus, the load correction factor K sub A is 0.8. Right? So I believe I'm confident that you have remembered this load correction factor for reverse axial loading. It is usually taken as 0.8. And then the endurance limit for reverse axial load is equal to the endurance limit times the load correction factor for reversed axial load times the surface correction factor. So please, while you're watching this lecture, with your pen and paper, please solve this problem in your own and check if and verify your answers with in the solution of this problem. So we substitute the value of K sub A, which is 0.8 for axial loading, and 0.9 is the surface finish factor, which is given as 0.9. Thus, we have the endurance limit for axial loading, which is 0.72 sigma sub E. Okay, so this is still this is variable. This is not yet known. So remember that the formula for the factor of safety is equal to the endurance limit of a material over the design stress. Since we are required to determine the design stress in this problem, we simply the expression is equal to the design stress is equal to the endurance limit over the factor of safety. So we simply substitute the expressions of the numerator and denominator. Thus, we already determined the expression for sigma sub EA as 0.72 sigma E, and we are given with the factor of safety 2. Thus, the design stress is equal to 0.36 sigma E. So since thus we have a variable answer in this problem. All right. So this is just for summary of this lecture. I have just discussed about the variable stresses in machine parts. So we first started off with the concept of the cyclic stresses. So the concept of cyclic stresses is that when a material, for example, or a beam is subjected to a load, there is a reversal of the induced stress into beam. So thus it is called as cyclic. And we also have different cases to which we call a cyclic stress into material. First is that uh, if the stress varies from a minimum value to a maximum value, uh, it is called the fluctuating stress. And also, if the stress varies from 0 to a certain maximum value, it is called the repeated stresses. And if the stresses vary from a minimum value to a maximum value of the opposite nature, say for example from a certain minimum compressive to a certain maximum tensile or vice versa, it is called alternating stresses. Also, I also discussed about the fatigue and also the time stress diagrams. And with time stress diagrams, uh, we determined the following the relations between stresses, the relations, for example, the relations for mean or average stress, reversed stress, repeated loading, the stress ratio R, and the relation between endurance limit and the stress ratio. And next is that we discussed about the different factors that will affect the endurance limit. What are these factors? The load correction factor or the load factor, surface finish factor, the size factor, and the miscellaneous factors such as the reliability factor, temperature factor, and the impact factor. And these different factors are usually taken with definite values depending on the type of loading, the type of loading, if it may be bending, axial, or torsional or shear loading. Alright, and next is that I discussed also about the relation between endurance limit and the ultimate tensile strength. Thus, we have some empirical relations between between the endurance limit and the ultimate tensile strength. We also discussed about the factor of safety for fatigue loading. So, and we also solved an example problem that considers the different correction factors or the factors that affect the endurance limit of a material and the relation of the uh, the endurance limit, and the design stress. All right. So this is all for the discussion in this video. Our next topic will be about stress concentration and more example problems. I have uploaded in the VCUEE the handouts for this topic. I have also uploaded there the handouts for you to read for the supplementary topics. Just navigate through the VCUE and you may download the handouts there. It is in PDF. And for the video about the rotating mirror beam method, for you to visualize and how it is done, it is embedded in the description below. Alright. So thank you very much for listening. See you to our next lecture.